Okay, so looking at the second question, it's asking us for A, it's telling us that if a hole is drilled inside of a cylindrical bottle, so like this, so on the side of it, so the water is going to be pouring out this way, like this. Um, the water, the height will decrease from 10 centimeters to 3 centimeters within 68 minutes. So this tells us that h of 0 is going to be sort of height at t0 is going to be 10, and then our height at 68 seconds is going to be 3. Um, we need to use equation 2 to find an expression for h of t. So this is going to be our equation 2 up here. In our case, our model was using 15 centimeters as its height, so we're going to be making h of 0, excuse me, h of 0 15, and h of 58.7 is going to be our um, our 0 when we have no water left inside our cylindrical tank. And using separable equations, we're able to anti-differentiate this and integrate it to find an equation for h of t. So, and then by isolating h, we'll get h equals kt plus c all over 2 squared. And this will be our equation for all of question A. So, using our initial values that we got here, we could plug in that at t equals 0, our height is 15, and we can use this to find c. Now using the fact that we have found c, we can use c to be able to find k. K is the physical properties of the liquid, so that's going to be, for example, how viscous, etc., as it says here, the rotation and viscosity of the liquid. So something that's a liquid that's maybe thicker will not flow out of a hole as fast as something like water. So, using our calculations here, we can use um, our second data point, which we know it's 0 at 58.7, to be able to find k. So all we have to do is we plug in 0 here, and we do equals k, and then times t, so 58.7 plus c, which is 2 root 15, all over 2 squared. And using a simple numerical solver on a calculator, we can find that k is going to be equal to negative 0.1319, or negative 0.132. Now, because we have all of the values we need to know for all the constants and all the variables we need to know, we have an h of t equation if we put everything together. So now that we have an equation like for h of t, we're able to make a table for t and h of t, as they ask us to get the values of h of t, meaning we want the heights for 10, 20, 30, 40, 50, and 60 seconds. That's question B. So question B asks us to actually carry out the experiment, so using a water bottle, uh, a cylindrical water bottle essentially, drilling a hole that's about 4 millimeters, um, and then filling it up with water and then letting the water drain out and timing it at stopping it at these intervals here every 10 seconds, from 10 centimeters until the the water essentially runs out. So for our cases, for our experiments, we did try to do it from a 10 centimeter mark, but after about 30 to 40 seconds, it was already over. And that's due to inconsistencies, as I don't think we were able to drill an exactly 4 millimeter hole. A bigger hole will obviously have larger volumetric flow and let more water out. So for our experiment, as I said before, instead of doing 10 centimeters, we've done 15, and even that barely got us towards 60 seconds. So, um, as we solved in the previous question A, we got K and we got our C, meaning we have now this equation here which represents uh, our our simulation, essentially our what our predicted values would be. Um, so this is what it looks like. So and then these are our experimental values. So here h of 0 is 10 is 15, h of 10 is 10.3, then 3.3, 1.25, 0.2, which are actually very similar to the values that we would expect here. 10.3, 6.5, 3.5, very, very close, but just not. So if we plot these points and we plot this experiment, this prediction graph, essentially, we can see our points from our experiment in green. So that it's going to be these right here. And then we can also see our experiment, our predicted line that it would that our water would go as. So what I find very interesting is here we see almost a linear pattern, almost as a constant slope. But as the water decreases by a lot, the slope actually starts to decrease as we start to see here, almost as if it's going to go like this, like a quadratic, as it's about to reach its minimum. This is because, as it was explaining before, when there's less water inside of a tank, it will be draining at a lesser rate, meaning that our rate of change is gonna be less. So our slope of this graph is gonna be less. So here, our slope here is way less than our slope here. So that explains why we're getting a curve, almost an x squared curve, one part of the x squared curve that as it approaches its minimum. Overall, this does a pretty decent job at predicting our values of our height as time goes on.